Thank you once again for coming to our lecture this morning. It's the day before Thanksgiving, and so it's kind of hard not to get into this mode of thinking about sleeping late and maybe just spending some me time. The Starbucks and other coffee shops sell drinks, lattes, things like that have these pumpkin spice flavors in them. And I'm not a super big fan of that flavor mix, but it got me thinking, if I walk into a coffee shop and I can smell this pumpkin spice, what am I smelling? I mean, it's not pumpkin. It's right, the pumpkin. If you've ever smelled pumpkin, it doesn't smell that great. It's these spices that they put inside there. So let's go ahead and take a look at the chemical composition of pumpkin spice, what you're smelling whenever somebody talks about the spices that they use to flavor pumpkin pie or a pumpkin spice latte. If you go into the kitchen and you prepare your own mix of pumpkin spice, it's going to be a mix of these 5 classic spices: 2 teaspoons of cinnamon, which comes from the bark of cinnamon trees, 1/4 teaspoon of ginger, comes from ginger root, 1/8 of a teaspoon of nutmeg, which comes from some sort of a nut from the fruit of some kind of a tree, 1/4 teaspoon of cloves. I'm not sure what kind of tree that comes from in nature, and then a 1/2 teaspoon of allspice, which is also comes from some sort of a shrub or tree. Well, what is it that you're smelling? You're not smelling the cellulose or the water or the kind of solid reagents that are in there. What you're smelling are organic molecules that have the ability to volatilize. So they have low enough molecular weight and they are nonpolar enough to make it into the gas phase and then into your nose, and then of course onto your taste receptors. So if you look at the major chemical that you're smelling from cinnamon, it's a single compound called cinnamaldehyde, and we use that in the Chemistry 51 LC laboratory. So a couple of weeks ago or last week, there was a laboratory experiment where you did crossed aldol condensations using benzaldehyde. Cinnamaldehyde, I think, was one of the aldehydes that you use. And if you go into a lab and you get a bottle of cinnamaldehyde off the shelf, it smells just like the spice cinnamon. It's the same molecule. No difference. Ginger. If you look at the main molecule that gives the characteristic smell, of course, all of these spices contain many organic molecules. I'm showing you the major volatile constituent in there. So ginger, the major volatile constituent that you're smelling is called alpha zingiberine. And you can tell from the name, somebody named it because it sounds kind of like ginger, because that's the characteristic odorant molecule. Whenever I see this, it makes me think, oh, maybe it could do an intramolecular Diels-Alder reaction between this olefin here and this diene over here. But that's not super facile. When you look at nutmeg, nutmeg actually contains quite a mixture of compounds. And the main molecule that's in there, the one that has the highest percentage of the composition, is this interesting cyclopropane molecule called saponine. And it actually occurs commonly in nature as either an enantiomer. That's not so common for chiral compounds. Usually nature makes one, or a plant might make one or the other enantiomer. So an interesting cyclopropane containing natural product. Cloves and allspice, the main organic compound in there that gives it their characteristic flavor is the same molecule, and it is called eugenol. And if I'm not mistaken, you did one of your first labs in the Chemistry 51 LC labs doing a steam distillation of eugenol from clove oil. That's exactly the way these are one of the main techniques is used to isolate these organic starting materials from plant oils. So how would you find, if you were interested in what is it that's causing the taste or smell of some fruit or some spice or some food that you're interested in, how would you find that information? How did I find this? Well, the key thing is to go over to a search engine like Google or Bing and type in composition. Composition means that somebody's going to tell you the list of chemicals that is inside there, and they usually give you the percentages. So that's one of the key search words that you use. And if you're interested in the composition of things that come out of these spices, then what you really want is the word essential oil. Again, you don't care about the starch or the amino acids that aren't volatile, or the lipids, or the cellulose composition. You're interested in the organic essential oils. That's what volatilizes into your nasal epithelium. That's what hits your odor and taste receptors. So you can see if I just type allspice essential oil in composition, I'm going to run into all kinds of websites that lay out in a percentage basis the chemical composition of these molecules. So enjoy your pumpkin pie or your pumpkin spice latte this holiday season. I'm quite sure that if you went to a chemical supplier and bought bottles of each one of these and mixed them together, it would remind you of a pumpkin spice latte. It wouldn't be containing all the constituents, for example, of nutmeg, but it would come pretty close. So we're in our last chapter here, chapter 23 for the course. This is the amines chapter, and we spent some time talking about nucleophilicity and basicity of nitrogen, and so we're really spending our time now to talk about basicity of nitrogen, and how easy is it to protonate or not to protonate some sort of an amine-containing compound. And I gave you a powerful equation for organic reactions where you're dumping chemicals into a flask and you're just allowing acids and bases to equilibrate. There's an equation you can use to estimate numerical ratios. And this is the way we think: 1 to 10, 1 to 100, 1 to 1,000. You think in numerical ratios. You don't think in log orders or powers of 10 or exponents. And so this powerful equation allows you to estimate equilibrium constants for any acid-base reaction where you know the pKs of the acids on each side. And all you have to do is some simple arithmetic, kind of the level at which I'm able to do it. pK of the products minus pK of the reactants, that's the exponent for the equilibrium constant. So if I'm able to use that, I'm sure you could do it too. Okay, so this sets you up to start thinking about understanding acidity and pKs, sets you up to start thinking about whether amines want to be soluble in organic solvents or in aqueous solvents. And this turns out to be an important concept for standardized exams like the MCAT, the PCAT, DAT, OAT, because you want to know, if you're some sort of a prescribing physician or a biochemist or even a chemist, you want to know whether molecules will end up in the aqueous phase or in the organic phase, or whether they will be able to cross biological membranes, which are like organic solvents, or whether they're going to stay in the aqueous layer or even be soluble. So, you know, one general principle for everything except really small molecules is that charged compounds, phenoxide anions, carboxylate anions, ammonium cations, charged compounds, organic compounds, will tend to be soluble in water. And if you partition them between water and an organic solvent, like gasoline or mineral oil or vegetable oil, charged compounds will stay in the water layer. In contrast, if you take a neutral organic molecule like phenol or a neutral amine, those are going to be soluble in the oil layer or in the organic layer. So if I take some sort of a molecule like pyridine, let me go ahead and draw up the chemical structure of pyridine here. Pyridine is just a cyclic amine. There's nothing special about it. The same conclusions you would draw if I were drawing triethylamine as an organic amine molecule. I can control whether that pyridine molecule goes into the aqueous layer or the organic layer. So, for example, if I want this pyridine molecule to go into the aqueous layer, then what I would do is acidify the aqueous layer. I would use hydrochloric acid. And every single chemist, organic chemist in the Department of Chemistry has a bottle of 1 molar hydrochloric acid sitting on their shelf for exactly this kind of reason. So they can extract organic amines into the aqueous layer. So, and in this case, under those acidic conditions, this would exist as the ammonium chloride salt. So, and the ammonium ion would be soluble in water. It would not want to go in the ether layer or the dichloromethane layer or vegetable oil or gasoline. So you just need to use acid to protonate the amine. Now, what happens if you don't want your amine to be in the aqueous layer? Well, then we could put the aqueous layer, we could make it extremely basic. Every organic chemist in our department has a bottle of 1 molar sodium hydroxide sitting on their shelf. Or you could just dump sodium hydroxide pellets into your aqueous layer here until it became basic. And then as soon as you do that, let me take out this. I hope you didn't draw that picture because I'm going to try to erase this. If you deprotonate the amine is then going to be soluble in the organic layer. There won't be any ammonium chloride salt left. The neutral amine will not want to enter the basic water layer because there's nothing to protonate it in sodium when you're in aqueous sodium hydroxide. And so in this case, you could just separate the ether layer and then evaporate off the ether solvent, and you would have pure pyridine. So again, you can control which layer your stuff is in. So if you want to get rid of an amine and throw it away, well, you extract with acid. If you want to isolate your amine as a pure organic molecule, well, then you wash it with base, and then you throw away the aqueous layer, and then you keep this organic layer and evaporate off the organic solvent. So powerful concept, this idea that you get to control whether amines go into organic layers or aqueous layers. Now, this situation that I'm giving you here is strictly for beakers and flasks where you dump in a vast excess of a strong acid or a strong base, sodium hydroxide or HCl. This is different from buffered conditions like serum that surrounds your blood cells or the cytosol of cells. Those are buffered conditions, and that's Henderson-Hasselbalch equation that you use to estimate what fraction is charged and what fraction is uncharged. Okay, this idea that you can take things that are protonated, like an ammonium salt, and then just treat them with base and get them to move into the organic layer is a pretty common technique that's used by drug users. So if you were buying a dime bag or something of cocaine, that white powdery stuff cocaine this weekend, what you're really buying, that white powdery stuff, is the ammonium chloride salt of cocaine, right? Ammonium salts are white and powdery, whereas neutral amines are kind of like oily, greasy, waxy things. They don't tend to be these fine flowing powders. The unfortunate thing about that nice white powder may look pure as the driven snow, but they are not soluble in organic solvents, and they don't cross biological membranes. And the whole point of these is that you want them to fly across the nasal epithelium and then make it into the central nervous system. So one technique for making these drugs seem far more powerful is that you'll take that white powder and you'll mix it with sodium bicarb, baking soda, Arm & Hammer baking soda that you buy. You just sprinkle a little bit of that on some aluminum foil with some sodium bicarb, and you heat the heck out of it. It doesn't work well because you don't have aqueous solvent in there. And what will happen is the bicarb is basic, and it will start to deprotonate this amine, this ammonium salt right here. And when you do that, when you deprotonate that ammonium salt, you end up with the neutral amine, the free base of cocaine. And we call this free-basing. It's not a drug term. It is a common term that's used in organic chemistry laboratories, that it is used in science. Anytime you take an ammonium salt and you deprotonate it with a base to create a neutral form, we call that free-basing because it converts ammonium salts, not quaternary ammonium salts, but primary, secondary, tertiary ammonium salts. It converts them into the neutral form, and those are now soluble in organic solvents. You can extract them into ether, into dichloromethane. They would fly right across the nasal epithelium. They are easier to volatilize, so if you're heating some aluminum foil with bicarb on a flame or something, the free base form of cocaine would fly right into your nose, right across the nasal epithelium, straight across the blood-brain barrier, and that's how you'd get a powerful high. So, and the byproducts of this would just sit there on the aluminum foil. That would just be salt, leftover sodium chloride from the bicarb and the HCl salt. CO2 would volatilize, and water vapor that's left over from the bicarb. Those would all just evaporate and go away. They're harmless things. All right, so this concept of free-basing to get things to go into organic solvents is a general concept. And I hope you don't ever use it for free-basing Coke, but that's what people are doing. If you see somebody shopping with aluminum foil and baking soda, you know exactly what they're up to. All right, I've already made the point before that amides are not amines. Amides with carbonyl groups are not amines. You can't think of them as amines. They aren't the same functional group as amines. And so what would happen if we took an amide and we tried to protonate this. So if we treated an amide with HCl, right, or some sort of an acid, it doesn't matter what the acid is, what's going to happen there? Well, to help you think about that, well, let me just go ahead and tell you what's going to happen. What's going to happen is that the business end of this molecule is not the nitrogen lone pair. The business end of this molecule is the oxygen. And so let's go ahead and talk about why you don't protonate the nitrogen of an amide. It doesn't matter whether it's a peptide bond amide in a protein or a carboxamide side chain of asparagine or glutamine. The place where you would protonate preferably would be on that oxygen atom. It will help us to understand that by first drawing out the resonance structure for this amide. Right? I can draw more than one resonance form. Here's the other resonance form. Whoops, I was about to draw a lone pair. It's already drawn in there. I would take that lone pair and donate it into the carbonyl. That's happening all the time. That's why that lone pair is not available for you to protonate it. It's not available for you to use it as a nucleophile. That's because that lone pair is already busy donating into the carbonyl group. And so let's draw that other depiction of this amide where we recognize that that nitrogen really looks like an N+ with no lone pairs on it. So how are you going to stick a proton on that nitrogen when it really looks like an N+? Linus Pauling, decades, half a century ago? I don't know how long ago, came up with a good estimate that the ratio of these structures is something like this. You've got about 40% double bond character, CN double bond character in an amide, like 40% of a positive charge on the nitrogen. So you're not going to be sticking any protons on that nitrogen. I mean, you look closely, if you wanted to stick a proton on there, you would protonate the oxygen. It's like O-, right? That's where you want to stick the proton. And so when you protonate that with an amide, this other resonance structure that I've drawn down below here really helps you think about that, about why you tend to favor protonation on the oxygen and never, ever on the nitrogen. You would never protonate an amide on that nitrogen atom. No known acid will do that. So, and this, again, we're just drawing a resonance structure of the product here. So, all right, so don't ever, never protonate the nitrogen of an amide. It's not possible. It's going to be hard for you to resist that. But you just have to understand this concept of resonance in amides. Now, this idea of resonance, you can put other acceptors here on the nitrogen and see the same deactivating effect, where you deactivate the lone pairs. And benzene rings can serve as pi acceptors. You can donate electrons from this nitrogen atom into the benzene ring. It's not as good as a carbonyl, but you'll see some of that effect. So when you put a phenyl group next to an amine, so that's called aniline, you really deactivate, not totally, but you partially deactivate that nitrogen. It's 100,000 times harder to protonate an aniline with a benzene ring nearby than just a regular alkylamine. So aniline is about 10 to the 5th less basic than cyclohexylamine or methylamine or triethylamine. Let's go ahead and take a look at how resonance deactivates that nitrogen lone pair and makes it harder to donate. So I'll draw a resonance structure here where I take that nitrogen lone pair and I donate it into that benzene ring, into the phenyl group. And so I'll end up with this resonance structure that looks like this. And now that you see this other resonance structure that has no lone pairs on nitrogen, it should be kind of straightforward to get this idea that, well, okay, I see why it's hard to put a proton on nitrogen. It's kind of like N+. But some of you may be saying, wait a second, isn't this other resonance structure non-aromatic? Why would that be a sensible resonance structure if you disrupt aromaticity? And you're exactly right. It is a non-aromatic resonance structure, right? That particular resonance form is not aromatic, but you know that this resonance structure must have some truth, because when you look at the rates of electrophilic aromatic substitution, we already told you that the ortho positions and the para positions of anilines are super reactive. That's exactly because of this resonance. This must be a good resonance structure because it exactly matches all of our observations for electrophilic aromatic substitution. And you can keep drawing resonance structures where you push this lone pair around that ring. I'm not going to draw all those resonance structures, but you get the idea. I'll just write etc. So anilines are not, it's not like they have zero basicity, but they're nowhere near as basic as a regular amine. You can still protonate an aniline. If I take a bottle of hydrochloric acid and dump it in there, I can protonate the aniline and extract it into the aqueous layer, but it's nowhere near as basic as an amine. I couldn't just take one equivalent of a weak acid like acetic acid and protonate that aniline efficiently. Now, when you put substituents, let me go back to that last slide. Just imagine how much more deactivated this nitrogen would be if we put electron withdrawing groups here on the ortho and para positions. Right? If we put on a functional group that could suck electrons, that could stabilize carbanions, then it would really make this N+ resonance structure super important. And so let's go ahead and talk about how substituents on anilines at the ortho and para positions, not the meta position doesn't have a big effect, but the ortho and para positions, those substituents can dramatically affect how basic those lone pairs are. Now, the challenge that we face, the unfortunate thing is we don't have tables of basicity. There's no such thing. We do acid-base titrations to get pKa's and acidity. There's table after table after table of pKa's and acidity. So, unfortunately, to think about basicity, you'll have to go back to the appendix of the book and look up acidity tables. There's a big pKa table. And then you have to kind of work backwards. And that's complex. That's a lot of complex thinking. I've tried to summarize here what conclusions you would draw about lone pair basicity by using the pKa's in the back of the book, in the appendix in the back of your book. So you can see that if you put a nitro group here at the ortho or the para position, so for example at the para position, and you draw the same conclusions if it was at the ortho position, the numbers would be very similar. Relative to just plain aniline, it has only H's on the benzene ring. Nitroaniline, paranitroaniline, orthonitroaniline is super non-basic. Boy, you would have a really hard time sticking a proton on here because that molecule looks very much like an N+ on there with no lone pairs. And same would be true if you put a carbonyl group at the ortho or para position. You really make that nitrogen lone pair on the aniline not basic. And you see kind of the opposite effect, not to the same extent, not quantitatively to the same extent, not a factor of 100,000, but a factor of 10 maybe. If you put a donor group at the ortho and para position, you see the opposite effect. Then it becomes a little bit easier to stick a proton on there. Now let's go ahead and take a look at some resonance structures to try to help us understand why you see these dramatic effects for substituents at the ortho and para positions. Not the meta positions, but the ortho and para positions. So if I put a nitro group over here at the ortho or para position, I can donate these electrons from the nitrogen lone pair all the way into this pi acceptor, this nitro group, and end up with a resonance structure that puts the negative charge, actually I'll go ahead and keep it like that. I was going to draw an intermediate resonance structure, but we don't need an intermediate resonance structure. We can draw this great resonance structure that puts negative charge on the electronegative atoms. Now, yes, the resonance structure has that resonance structure over here is not aromatic. That's true. But at least I get to put negative charge on electronegative atoms. So that's the most important resonance structure you can draw. And when you look at that resonance structure, I hope it's obvious, yeah, how are you going to stick a proton on that nitrogen when this resonance structure is just so amazing and awesome? Look at that. Negative charge on the most electronegative atoms, on oxygen atoms. That's a great resonance structure. And unfortunately, that resonance structure has no lone pair on the NH2 group. Now you'll see the opposite effect if you put an atom with a lone pair donor at the ortho or the para positions. And so let me go ahead and draw out the lone pair on that methoxy group, or if you had an amino group there. Now we have to think about think about the effect of that lone pair on the basicity of this nitrogen atom. So now when I try to draw resonance structures starting from this NH2 lone pair, I'm going to be able to push electrons into the benzene ring. I'm going to be able to push electrons over here to this other double bond. But then I have to stop. I can't push any electrons into this oxygen. That oxygen already has 8 electrons. And I'm not going to violate the octet rule. Nothing can violate the octet rule. So I'm going to be stuck with a resonance structure here where I end up just depositing that lone pair right there on that carbon atom. And that's kind of frustrating because now you're going to end up with a resonance structure that doesn't look so good. That other resonance structure is going to have a carbanion right next to another lone pair. Right? They're both trying to donate. Like, which one is going to donate? It can't donate here. This lone pair over here, it's just super frustrated. So this is not a good resonance structure. This is a pretty poor resonance structure. Let me just put a sad face there for that resonance structure. Which means if that's not a good resonance structure, then there must not be a lot of positive characters. So when you put a methoxy group out here, opposite para to your amino group of the aniline or ortho, that methoxy or that lone pair donor makes it easier to protonate. It frees up that lone pair so that lone pair is spending less, essentially, time donating into the benzene ring. You know, it's hard to draw all the resonance structures and work all the way through pKa's to match up these effects to pKa tables. But that's the kind of thing they put on these standardized exams where you have to draw out a zillion resonance structures, draw conclusions about the acid-base equilibrium, and then try to take your conclusions about basicity and match them up to an acidity number, a log order acidity number. I'm not going to make it sound like those problems are easy. Those problems are a lot of work to think through. So I get that. Okay, so resonance effects on acidity and basicity. Right? You want that lone pair to be free and available if you want to use it as a base in a reaction instead of sucking the lone pair away using resonance. Let's go ahead and take a look at another effect that has nothing to do with resonance but can be quite powerful. So resonance has powerful, powerful effects on reactivity. That's why I talked about resonance first before this effect. But this is an effect that somehow they just seem to have missed this important effect in the book. I think they just mentioned it briefly in one of the earlier chapters, didn't explain what it was for or how it would impact things. And so I want to talk about hybridization, SP, SP2, SP3, and what a dramatic impact that has on chemical reactivity. Every single time I have drawn an oxygen or a nitrogen in this class, I am instantly thinking about the hybridization of that atom. And if you're not thinking about the hybridization, you're missing one of the most important factors about chemical reactivity. I'm going to take 3 different nitrogen atoms. All of them have lone pairs on them. Here's an alkylamine with a lone pair on nitrogen. Here's an imine with a lone pair on nitrogen. And here's a cyano group, a nitrile with a lone pair on nitrogen. They all have lone pairs. They're all nitrogen atoms. You know where nitrogen is in the periodic table. But if I look at those lone pairs, they have different types of hybridization. And I want to look at that hybridization. So an amine has sp3 hybridization. An imine has sp2 hybridization. And a nitrile has sp hybridization. And the key feature of this hybridization is p character. Different percentages of p character. On the top here, that's 3 parts p. The recipe is 3 parts p orbital, 1 part s orbital, and that's the recipe for making an sp3 orbital. 75% p character. The recipe for making an sp2 orbital is 1 part s orbital, 2 parts p orbital. That's 66.6% p character in that lone pair orbital. And the recipe for making the sp orbital is 50% s and 50% p. 50% p character. P character determines nucleophilicity and basicity. Let me just write that down. P character equals nucleophilicity and basicity. The more P character you have, the more nucleophilic, the more basic. P orbitals are high in energy, S orbitals are low in energy. High energy things are reactive, low energy things are not reactive. It's a pretty simple idea. Let's take a look at the impact here of this difference in P character, this difference in hybridization. If I look at the relative basicity, which I can back out using a pKa table, let me compare both of these, all three of these compounds to just the amine. I'll just arbitrarily assign that a relative basicity of 1. Now, an amine has more P character than an imine, 75% versus 66%. And so what does that do to the basicity? Because of that difference in basicity, whoops, let me do this in red because I started the first one in red. That the sp3 lone pair is 100,000 times more basic than the sp2 lone pair of an imine. That tiny bit, that tiny extra 66% P character versus 75% P character leads to this huge difference in basicity and nucleophilicity. And you may say, well, you know, when am I ever going to work with methylamine or a simple imine? Never. You're not going to see those again. Nobody cares about those molecules. But what you will see is molecules, for example, like triethylamine. That's an sp3 hybridized amine. You may see molecules like pyridine. That's an sp2 hybridized amine. Right? Triethylamine is vastly more, way more basic than pyridine. Pyridine is just kind of good enough to soak up HCl. Triethylamine can actually pull off protons from OHs to a small extent. But so you might have noticed that in some recipes we use triethylamine when we acylate things with acyl halides or anhydrides. Sometimes we use pyridine. And we're choosing those based on the basicity of the lone pair because those nitrogens have different hybridization. Now, when I get down to sp, where it's only 50% P character, you've just decimated. It's very, very hard to stick a proton on an sp hybridized nitrogen. I can't even see what I've drawn here. Let me just try to count this out using. I think that's 15 zeros. Does it matter? I mean, if I drew 14, would you draw a different conclusion? It's like 10 to the 15, less basic. Boy, if you want to do anything that involves protonation of an sp nitrogen, you're going to be dumping in sulfuric acid, you're going to be heating things, it's hard to protonate an sp hybridized nitrogen. So it's not like nitrogen is nitrogen is nitrogen. The hybridization of these nitrogen atoms and oxygen atoms matters for every molecule that you've been drawing throughout this whole course. If you haven't been paying attention to hybridization, I don't know how you've made any sense out of what we've been talking about from throughout organic chemistry. Okay, so I want to kind of take these ideas a little bit and try to move into a different effect that's not exactly hybridization, but I want to talk about heterocycles, nitrogen-containing heterocycles. So let me just kind of put a title here. I'm sorry I didn't have a title here. So let's go ahead and talk about nitrogen-containing heterocycles. These same types of principles would apply if you were talking about biological molecules like indole nitrogen, adenine, cytosine. So the general rule we have, like if you're looking at some nitrogen-containing heterocycles, this is called pyrrole, this is called pyridine, this is called imidazole. So you find pyrroles in the side chain of tryptophan. I don't know where you find pyridine. Pyridoxal phosphate is one of the cofactors that you'll see in biochemistry classes. Imidazole, of course, is a side chain of the amino acid histidine. How would you decide whether you can protonate easily the nitrogens on these heterocycles? They're all aromatic heterocycles. And I'm giving you two simple rules that you can use to figure that out. So first simple rule that we have is that if the lone pair on if the nitrogen atom is attached to a double bond, then that nitrogen is not basic. So if you have this arrangement, if you have a double bond and there's a nitrogen attached, that nitrogen is not basic. And this is particularly true for heterocycles like pyrrole here. This nitrogen atom, It's got lone pairs, but it's not basic. You can't protonate that nitrogen atom. It's not that you can't protonate pyrrole. If I use sulfuric acid, I can stick a few protons on a few of the molecules, but this is basically, essentially, it's an enamine, and enamines protonate here. They protonate on the carbon atom. That's where they protonate. It's not the nitrogen that picks up the proton, it's the carbon atom. And you can draw resonance structures to remind yourself of why that's true, right? When you protonate that with an acid, you protonate on carbon, not on nitrogen. So don't try to protonate the lone pair of a pyrrole, because that's just not basic. If I come over here and I look at my second rule, if the nitrogen is part of a double bond, then it's a little bit basic. If it's part of a double bond, right, like this down over here, then it's a little bit basic. Why isn't it super basic? Well, because it's sp2 hybridized. So it's a little bit basic. You know, it's still, you know, it's still available for protonation. It's not caught up in resonance, right? You might think, oh, gee, can't I donate that into? No, the lone pair is sticking out the side of the benzene ring like an arm, whereas the pi electrons are up and down. Those are orthogonal. There is zero net overlap between orthogonal orbitals. So just with that simple rule, without drawing out pictures, if the nitrogen is part of a double bond, it's a little bit basic. And the basicity is a little bit reduced because it's sp2. Now, when I look over here at imidazole, I've got both types of nitrogen. I've got this nitrogen that is part of this double bond here, so that's going to follow this second rule. It's part of a double bond, so it's a little bit basic. This other nitrogen on the other side is attached to two double bonds. It's not, this nitrogen over here on the other side of the imidazole is not part of a double bond. It's attached to double bonds. And so that nitrogen right there is not basic. And it doesn't matter whether it's attached to a CN double bond or a CC double bond. You would never protonate those two nitrogens equally on a histidine side chain. When you look at every single enzyme that we know about, I don't know if you talked about the importance of imidazole in catalytic triads, in proteases, but every single crystal structure that we've ever gotten for every single enzyme that uses a histidine side chain to pull off a proton, the enzyme always uses this nitrogen to pull the proton off. It never, ever positions the other nitrogen. Nature's very clever. It knows all these rules and uses these rules in catalysis. All right, so there's two sections in this book that you can read it, interesting, but I'm not going to ask you about it. The first one is stuff we've already covered, and that is that amines can act as nucleophiles. Amines can attack carbon. They can attack carbonyls, so that's kind of a review. The other section has to do with this archaic process called the Hofmann elimination, which people were using about almost 2 centuries ago. People don't use it anymore. It's not useful for anything. I don't know why they cover it in the book, and there's a zillion questions in the back of the chapter where you make quaternary ammonium salts and use silver. It's just not a useful process, and you can certainly read about it, but I would never ask you questions about that on my exams. But what I do ask questions about is the chemistry of nitrous acid and arene diazoniamides. This is the last section of this chapter that is important, and you need to know these reactions of amines with nitrous acid, and particularly aromatic amines, anilines. Let me go ahead and talk about nitrous acid. This is an acid that I don't think you've ever heard of before. Certainly we haven't covered it, and nitrous acid is not the same as nitric acid. Nitric acid has 3 oxygens. This is nitric acid. We've talked about that before. But nitrous acid is missing one of those oxygens. And sometimes it's written out as HNO2. Let me draw that somewhere here, HNO2. That's one way you can draw that using a molecular formula. Quite often it's written to show the connectivity of the atoms as HONO, H-O-N-O. You can type that out and make a text message writing H-O-N-O. That also means nitrous acid. But let's go ahead and talk about nitrous acid. Like, why haven't we talked about that before? How come nobody's made any mention of that? And the problem is you can't buy nitrous acid. There's no bottle of nitrous acid that anybody will sell you. You have to make that yourself in the lab. And it's not that it's hard, but there's no such thing as going to your chemical supply, at least as far as I know, and buying nitrous acid. What you do is you make nitrous acid yourself. You mix two salts, well, you take the salt, sodium nitrite, and you mix that with hydrochloric acid. Sodium nitrite's just this white powder, it's a salt. You do these in water because it's aqueous HCl, and sodium nitrite is soluble in water. And that's how you generate nitrous acid. Let me go ahead and draw out the Lewis structure of nitrous acid here. There's a lone pair on nitrogen, so the nitrogen satisfies the octet rule. So that's nitrous acid, and you're just protonating one of the oxygens that has the O-. There's also sodium chloride there that's generated, but that's not at all interesting. Let's go ahead and talk about what's happening here, the mechanism for this. It reminds me a little bit of making nitronium ions when you do aromatic substitution reactions to nitrate benzene rings. The mechanism involves protonation not on nitrogen, right? You are protonating the nitrogen, but I'm only going to show the steps that lead to the formation of the most interesting species in this reaction mixture. The interesting species that is generated in small amounts, the one that does all the work, is this thing called a nitrosonium ion. Let me go ahead and draw out that nitrosonium ion. Here's the Lewis structure for a nitrosonium ion. So when you synthesize nitrous acid and have this solution of nitrous acid, it's full of nitrosonium ions. They're floating around, they're in equilibrium. And they're going to react with amines if you put an amine in there, those nitrosonium ions. Let's go ahead and take a look at the mechanism for forming nitrosonium ions. It looks a lot like making nitronium ions in electrophilic aromatic substitution. So if we have some sort of an acid in there, like this, you protonate the oxygen every once in a while. Now that bothers me because, I know for a fact the nitrogen lone pairs are more basic than that HO. But unfortunately, when you stick a proton here on the nitrogen, there's no mechanism that will ever take you here. I'm not saying you don't protonate on the nitrogen. I'm just saying that that's not going to lead you to any explanation of nitrosonium ions, and that's what we're trying to explain here. So when you protonate there, you turn that OH into a good leaving group. It's now ready to leave. And there's a lone pair over here on oxygen that has just been sneakily waiting for you to protonate that OH. Just hanging out, waiting, and the second you protonate that OH, boom, it's gone. And so that's the mechanism for why you have this equilibrium quantity of nitrosonium ions, right? You generate water as a byproduct. The water's coming back in and attacking and taking you backwards, right? This is all reversible. You don't have to draw the reversible arrows there, but all of this is in equilibrium. When you make nitrous acid, you've always got a small amount of those nitrosonium ions. Now if you throw in an amine into a mixture into nitric acid that has nitrosonium ions floating around, those amines will just like the water will reattack and go backwards, amine lone pairs can also attack nitrosonium ions, and they do not go back. That does not go backwards to regenerate the nitrosonium ions. So when you treat amines with nitrous acid, those nitrosonium ions will add to the nitrogen atom. Let me go ahead and draw out this initial intermediate, the initial mechanistic intermediate. Initially, you'll get this this nitrosylated ammonium species here, and then we simply use the counterion from the nitrosonium ion, probably chloride under most conditions, or water. You don't know actually what it is. And that will deprotonate to make what is called an N-nitroso compound. And specifically, if we just nitrosylated amine, well, I've already got the name written over here. This is called an N-nitrosoamine. Boy, those are spooky looking to me, right? If R or, let me just go back. If R or R prime is equal to methyl, oh, that's cancer. That's going to be a cancer-causing chemical. You do not want to be forming N-nitroso compounds from N-methylamines. You have metabolic enzymes that'll take that amine and try to chop it up, and in the process they make a potent carcinogen, and you can't stop that from happening. So be on the lookout anytime in your life. There's not that many things that scare me, but the things that scare me, you know, I'm wary of all the functional groups that can really do me damage, and N-nitrosomethylamine is a recipe for cancer. And for mutations. It will methylate your DNA and cause mutations because it will overwhelm the repair systems that you have. Okay, I have to stop right there because we don't quite have enough time for me to show you how this nitrous acid is useful. When we come back on Monday, after you're done studying all weekend for our exams, I'm going to tell you about how you take anilines and convert them into these things called arene diazonium ions. And we're going to be able, I'll give you 5 recipes for things that you can do with those. 5 powerful recipes that are extremely useful. So you guys have a great long weekend. Study like crazy because this is our last chance before exam 3. This is our last weekend before exam 3 for you to study. And so you need to get on top of that. And we'll have some extra study halls this coming week, next week.